the Whiting School of Engineering at Johns Hopkins University, and she's also affiliated with the Johns Hopkins Mathematical Institute for Data Science and the Johns Hopkins Institute for Assured Autonomy. Her research interests are in machine learning for trustworthy AI, and she's broadly interested in developing principled machine learning algorithms for building more reliable, trustworthy, and human-compatible AI systems in the real world. So I'm really excited to hear her talk with the title Distributional Robust Extrapolation for Agile Robotic Control.
Okay. Thanks, Sarah, for the introduction, and thanks for the organization of the workshop. It's my great pleasure to be here. I'm very excited because it's actually my first in-person talk after how many years, like after COVID. So, and also my first time attending RSF. So really thanks for the invitation. Today I'm going to talk about distributional robust extrapolation for agile robotic control. So my background is a machine learning one, but I'm very fortunate to have been working with robotic and control researchers in the past few years. So when we have listened to like control talks, and in this talk I'm going to first talk about machine learning and switch gear a little bit, but also eventually we're going to talk about control and finding problems. So machine learning has been an important component to many trustworthy AI systems that concerns significant societal impact and human safety. For example, in self-driving car perception, like this perception depends a lot on this image classification, segmentation, and object detection kind of algorithms. They're all based on machine learning algorithms. And then control experts are also trying to use machine learning to model like unknown dynamics or how to model kind of dynamics in dynamical systems. So the applications include, for example, drone control, safe drone control, or even like safe planning for the spacecraft. However, a conventional machine learning algorithm cannot be directly used in those scenarios for several reasons. The first failure mode can be our data uses always violate our assumptions. So in conventional ML, we usually assume our training data is a very good representation of the testing. So usually you have this train data, you train a model, and then test on the same distribution. But then in the real world, it's so often that you have very clean images, for example, in vision problems for training, or have blurry and noisy ones in the real application. Also, it's very easy and also cheaper to just collect and train models using the synthetic models, like with them indicate black and white images. And you have this 3D model that's very easy to generate those things. And it's much harder to directly deal with, for example, noise and colorful real world. So when this happens, we just say that there is a distribution shift, or the dataset shift, or domain shift. There's possible different names in the literature about it. A second failure mode can be there are constraints in those applications that this machine learning system needs to satisfy. For example, if you want to land a drone, for example, you may want it to land smoothly. That means the drone maybe touch the ground with a slow speed. So that's like land smoothly with some constraints, can be formulated as some constraints. Or if you think like braking a drone is not that big deal, how about the drone can hit a person? So you want it to stay away from human. And then in spacecraft navigation, you also wanted to navigate space without collisions. These are all these kind of constraints. And when there's sequential decision making and also iteration in the process, these two failure modes can actually happen at the same time. For example, let's say you want to put a Mars rover on Mars. It may have seen some safe space, for example, in data on Earth, let's say. But then when it's really put on Mars, it probably can need to explore something it has never seen before. So every step of exploration can be regarded as a distribution problem. You're saying you're deviating from your original training data. But then things get trickier when there is a safety constraint or there's an unsafe region. This Mars rover is too dangerous for this Mars rover to really approach. So if we do not really deal with this distribution problem in a principled way, we cannot, for example, differentiate this unsafe versus safe regions. So I think the key question here is like, how do we extrapolate to a new domain, to a new distribution, and also how confident our model should be. Let's say in this example, if this Mars rover sees some rock on Earth or in the training data, when it's actually on Mars, it maybe sees some like new rocks it has never seen before. Then how confident I should in this new domain? And I argue that if we have the right way to extrapolate, we have the right amount of confidence, we can do a lot of things in this case. For example, first thing, if I have the right confidence, if I fail, I should fail gently. So that means even though I may not be able to recognize these new rocks, I will not predict as something else with very high confidence. So I feel more gentle. And the second thing is like if I have the right amount of confidence, I may be able to check the constraint satisfaction in a new domain and then try to avoid those dangerous regions. And finally, and I think also very importantly, like if I have the right amount of confidence, I can use that uncertainty model to help me collect more useful data in a new domain to help me adapt. So the high level research questions I'm really interested in is like how do we produce good amount of confidence on the distribution shift? And then how to translate those uncertainty and confidence into constraint satisfaction, and then also how to integrate those machine learning models into real-world decision-making systems. So in the past few years, I've been working on this distributional robust learning framework and its applications. I've been working to apply this method into a safe landing problem where we achieve this fast and smooth drone landing even without human supervision. Extension of this work is a safe planning problem where we achieve this trajectory optimization under safety constraints. So in this talk, I'm going to first introduce some fundamentals of distributed robust learning. It's a very classic but also new kind of framework. And then I'm going to talk about how do we apply this to self-safe exploration problems and with a drone landing application, and then also another like safe planning problem for the spacecraft. And then finally, we'll talk about some takeaways. So let's take a look at some fundamentals first. So let's say we're dealing with a regression problem on the distribution shift. So in this case, I say we have sort and target distribution. Sort is a training, target is a testing. And let's say I have some data points, which is the blue dots. So a very intuitive way is like let's just train a regression model, and then here I'm showing you the extrapolation of this linear regression model to the target domain, and also the dashed line is somehow the confidence interval, let's say. But then when it's actually you see the ground truth model and also the target domain data, which is the green triangles, you can see that there's a big gap between your extrapolated like linear regression model and the ground truth. So imagine how bad it can be when it comes to safety critical cases when you have this kind of large errors in your target domain. So maybe a better solution is like we have a larger confidence interval, which is more conservative in the target domain when this target data have less support in the source domain. Let's say Y is maybe a better solution. So in this case, we assume we have some labeled source data. We have X and Y in the source domain. And then I have some input source and target distributions. This proposed solution basically, when it goes to this right-hand side, it gets larger and larger confidence interval when this target is far away from the source. So the idea is like, so I'm going to give you this proposed predictive form before I trying to justify this. Why it is the right thing to do? Why is the good thing to do? So in this case, we have certain target distributions, and then this proposed prediction form looks like this. It's an exponential family with a density ratio and the potential function. And this density ratio is source over target. And then if you look at this, the uncertainty will goes up with density ratio goes down. So extreme case can be, for example, this density ratio is like close to 0, then you have a very non-conservative distribution. But then if the density ratio is high, that means the data has higher source support, then you have higher certainty. So the intuition here is like we want to give more uncertain prediction, more conservative prediction on the samples that's farther away from this training data. And how do we measure this kind of distance? We use this density ratio, which is source over target. And now let's just try to justify this. What is the right thing to do? Before I go to the math of this framework, I want to give you another very extreme but very simple like calculation problem. Let's say we have like a yellow banana and red apple. That's your 2 data points in training. It's very extreme example. So you have source data, and then in the target domain you have a yellow apple instead, but you also only have the input, so which is the color. So then you know that the difference between source and target in the color distribution. What you want to do is like, can I predict given this color whether it's a banana or whether it's an apple? So a popular learning framework is empirical rationalization. The idea is I have some training data. Assume this data basically approximate my real distribution, the distribution I care about. Then I directly try to optimize a predictor function in this empirical data, but assuming this empirical data is an approximation of my like expectation, which is my ideal data distribution I care about. So then if you apply this kind of empirical rationalization into this very naive kind of 2 data points example, even this kind of data points, very tempting to say, even this yellow color is a banana, given this red color is maybe an apple. Then if you have a yellow apple in the test, you'll say the banana was very high confidence, right? An alternative of machine learning framework is called the distributional robust rationalization or the adversarial rationalization. There's kind of different ways of calling it. The idea is like I still have training data, but I ask this question: is this really good data? Is this like really reliable data that approximate the distribution I care about? Maybe not, but at least we can extract certain feature statistics from it. Let's say I see the certain first moment kind of features from it, let's say, and then I input that into some adversarial player who try to play a game with the predictor player. So this adversarial player can perturb the distribution while still satisfying certain constraints from this feature statistics. So the definition of robustness here is like this predictor try to play this game and will achieve its best payoff of this natural equilibrium while playing with this adversarial player who is compatible with training data. So in this case, the predictor does not really have access to data, but the data is used to constrain this adversarial player. So a closer look in math. It's actually a very classic framework. So it looks like this. We have a minimax game. The main player is this P hat, y0 x, that you're doing a regression problem. And Q is this adversarial player, try to maximize the loss function. And then you have this one, there's no distribution shift. You may see that the data that you use for the constraint Q, and also the data to define your loss, expected loss, is the same distribution. So in this case, it's the source data distribution you have in your classification problem. But what if they're not the same distribution? Let's say I care about the target, because I know there's possibly a shift in the target domain. I know the source data may not cover everything that I care about. So when there's distribution shift, you still have this minimax game, P and Q, and Q also happens to be here. So if you're not quite familiar with DRL, it's like usually have the adversarial player in the expectation the cost function or the loss function here in this case you care about. So then you have shift. That means I still have source data that can constrain my adversarial player. But then I care about a loss function on the target domain, which is in this case you have target distribution in the loss expectation. And then in this case we can directly minimize the loss on target domain, even though we do not have any labeled target data or labeled test data. So the recipe we're using this kind of framework is like you need to first choose the loss function that you care about, and then you kind of construct a constraint set using certain features. Let's say it can be linear features, high moment, kernel functions, or even deep neural networks. And then you just try to solve this minimax game and try to derive a learning algorithm from this kind of minimax game. So there are several properties I want to highlight of this framework. The first property is like in some cases, there are easier solutions for this min-max game. It looks like very complicated, but in some cases, it's easier than others to solve. So in this case, we use log loss, for example. And also, if we use a constraint like feature expectation matching, that means I choose a phi function as my feature function, and then I make sure that this expectation under Q, which is my reversal player, is matching the expectation under this, because it's the like data distribution, chain data distribution, matching chain data distribution. And in this case, we can basically derive an analytical form for this from this min-max game. And it's in this case, it's this exponential form that I showed you before. And you have this density ratio try to adjust your uncertainty according to how far away example is like cover is from source and target distribution. And then this one is this previously is the classification problem. Here comes the regression kind of case. Very similar, it's just you have a slightly different loss function where you have a base predictor set by the user. That's kind of like the prior thing. Like for example, when data is not very reliable, you still have to predict something, and then that's basically your safety choice or kind of default choice. You have the same analytical form, you have the same constraints, and then you get this kind of analytical form. They have two components. One is this prior knowledge kind of base distribution P0, and the second part is then the same thing as the exponential family kind of form, and this represents information from data. A nice property from this is like if you use specific phi function, which is the feature, and P0, which is the base, you can directly derive a Gaussian distribution from it. A second property, which is basically the key property we want to also talk about here, is the conservative uncertainty. So let's say in this classification problem we talk about, right, you have this label source data and input source and target distribution. Under this kind of framework, since you can look at the density ratio of the source over target, even though you will predict a banana as a wrong label, you still have a more conservative confidence. For example, in this case, you're closer to this uniform distribution, 0.5 kind of distribution. And in the regression case, is the example we have shown before. So in this case, you have a linear regression that's very optimistically extrapolation to the target domain. But this robust regression kind of formulation will basically give you this larger confidence interval, because when you get farther away from source, this density ratio gets like smaller and smaller. And the third property is that you can also looking at the learning theory and then try to bound the learning error. In this case, we assume the model is linear. So basically, we're using linear phi function in our previous framework, and then can bound this learning error in terms of like the upper bounds of density ratio, and also the slack value in your constraints, and also upper bound on the features and parameters. So typically for this part is like, in this learning framework, we try to give uncertain predictions on the example that's far, and then unless being told now to even more prior knowledge by the user. In the regression case, if you, for example, give a very certain base distribution, they still can probably give a very base prediction. It's just like if you only depend on data part, it can be like very pessimistic. So this is the first basically the first part of the learning fundamentals of this DRL. Any questions? Okay, so next part I'm going to show like how we apply this to achieve safe exploration and also safe planning. So I want to first motivate this application. So in this case, I'm showing two videos. One is the drone is like smoothly landing, and that means it touch the ground with a small velocity. Well, the red one is like a very aggressive landing. It's like how this got bumped on the ground. So we want to achieve this smooth but also safe landing. But then there's a learning problem here. So when the drone is like very close and with also relatively high speed, when it's close to the ground, then there's this kind of ground effect between this drone and this ground, and then it's usually hard to model using physics. So my control collaborator said, how about we use a mixed kind of like dynamics model to model it. So the first part is a nominal physics model. The second part is kind of aerodynamics part when it's very close to the ground. It's like you don't have ground effect. How about with a machine learning model to estimate this component? And also in this case, we want to achieve this fast but smooth landing. That means if you do not really, you can maybe slowly land, but safely land, that's no problem. But then can you really achieve a generally fast but smooth landing? That means you need to try to predict the aerodynamics when you are close to the ground. So these three types of landing, you can look at this curve. The green one is very fast but unsafe. Maybe you have a big bump here. The blue one is the slow but safe one. But we want to achieve something in between, which is maybe even hard for humans to really operate the drone to achieve this kind of smooth but fast landing. So as this question, can we achieve this by letting the drone explore itself? That means when there's no human pilot data collection. And why distributed robust extrapolation is relevant here is like, let's say the drone can maybe do a slower landing and it's easy for human also to do it. But then if the drone try to explore faster and faster speed domain, it may hit a wall, which is like there may be some safety constraint, which is when you touch the ground, you probably cannot really have very high speed. So there's safety constraints here you need to specify. And if you're too aggressive and overconfident in your extrapolation, you may try to collect data with like very high speed, and that's maybe not safe. And then in dynamic learning problem here, we're trying to have a mapping between like position, velocity, and orientation to the ground effect. So essentially it's a covariant shift problem in dynamic learning. Covariant shift means like this y-given x, this underlying model, true model in this case, is not changing. It's just you're seeing data only in the slower domain, not seeing data in a faster domain. So only the input distribution is changing, but not the underlying conditional, for example, y-given x in this case. Distribution is not changing, so it's called covariant shift. So basically, we want to use this distributed robust learning for accounting for this covariant shift in dynamics learning, and then we have this kind of recipe for learning and data collection. The idea is like I first have a pool trajectory and also an initial model, and I use this model to make prediction on my pool. Let's say we have a design trajectory pool, and then we check safety for each of that. And then we only query the safe samples that minimize my lagging time, and I retrain the model. The tricky part here is like how do you check safety, right? And the lucky thing is like in the if we use distributed robust learning and also try to use a specific type of controller, which in this case a data generalization controller, we can actually approve some tracking error guarantee. So this just says the trajectory will exponentially converge to a tube with the width with a constant times the maximum learning error. And this maximum learning error is from the DRL framework. And then this constant is related to certain parameters in the controller. So basically use this gamma times epsilon m as our worst case, as our possible worst case trajectory. And we only check the worst case trajectory whether it's safe or not. So let's see how it works in a simulation. So in the first epoch, we can actually see that the drone is like hovering there and cannot really land because you have this ground effect that just push you up, and you cannot really cancel that out and cannot really touch the ground. But after 10 epochs of learning and data collection, we basically can achieve this like fastest landing is usually like 1.6 seconds, and then you also try to avoid unsafe region, which is in this space plane, which is this area when you have higher velocity than some threshold. In this case, 1 meter per second. So you try to basically directly try to stay away from this unsafe region, just to satisfy your safety condition. And we will converge to this fastest landing time in our trajectory pool in 10 to 15 epochs. We also try to compare with Gaussian process, which is a very popular kind of learning algorithm in dynamics modeling in learning control. And then we find that Gaussian process is brittle in high dimensions due to poor choice of kernels and priors. So in this case, we can see that our method basically outperform the Gaussian process and different kernels by a large margin. Okay, I got 3 minutes time limit here, so I probably will just skip this part. Basically, I just want to cover just a little part in this part. Basically says in the second extension of this safe planning problem, we instead of have a directory pool, which is human design, we use a optimization problem to directly optimize this directory under some uncertain like dynamics model. In this case, you have a information cost that's based on your current then model. You have constraints from your uncertain dynamics model, and also Charles constraint that just basically characterize like where is this unsafe region and where you want to stay away from those. And then this is just a glimpse of the results. Like we can see like we tune the different kind of cost weights, then you can see like a different kind of directories, but they both stay away from the two gray block, which is the obstacles in this case. I'll just skip this part. Okay, so the takeaway for this kind of application kind of section is like we look at distribution problems, and it's inherent in the analytical learning for safe exploration if you really need to explore this new domain. And then we try to reason how linear guarantees can be translated into control guarantees under some constraints. And also we use this control guarantees to check safety and choose the next data for next round of learning. And then we conduct like experiment in simulation design from real drone data. This is something I forgot to mention, which is in our simulation, we also train our underlying ground effect model using a real like drone data. So not only like physics based. Okay, so the main takeaway here I kind of want to convey is we want to deal with distribution shift in a very principled way. And then in this case, it basically facilitates this control guarantee and also safe exploration in safe landing problem. And then how to deal with shift in a principled way? In this case, we introduce a method called distributional robust learning and try to quantify domain gaps with density ratio and make sure the model extrapolates accordingly so that it helps us constraint satisfaction and also end-to-end guarantees. Okay, thank you very much for your attention, and then I'd like to take questions.
We have questions. Yeah, you were first. Yes, wait, I bring you the microphone.
For the talk. I was curious about, I guess, I'm not sure I like totally understood what exactly you needed from, I guess, the shifted distribution in order to do this. Like whether, I think you said you don't need labels, but exactly like how far can the shift be? What sort of information about that do you need?
So actually, there's two parties like so we need to source label data. We need to like we need at least some unlabeled target data so that you kind of know how far away you try to extrapolate. Because if there's nothing there, well, we're also working on a follow-up work when there's nothing about target. But in this case, we're still using target so that it can estimate the density ratio. So in Java, you can think about label source data and some unlabeled target data to estimate the density ratio. And if you look at the balance, is also give you something that is going to reduce your guarantee. And to be honest, this bound can be a little loose because you have upper bound for density ratio, which can be very loose. Luckily, in some problems, you can even control your target domain so that it's not that far away. Like for example, in our configuration, basically, like you're choosing your next domain to extrapolate to. So maybe you can make this less make it more meaningful. Because sometimes it can be a very loose stuff. Yeah, that's basically you still need some data to estimate the density ratio and that no definition.
Yeah, thank you.
Yeah, thanks for the really great talk, Anqi. So if you look at this figure, right? So we clearly have the source region and target region, and in your also like the demonstration you showed landing, you also kind of have this is source and this is target. But in general robotics applications, like we really do not have that kind of separations, right? Sometimes like always somewhere in the middle, like it could be out of distribution. And so your distribution could be really weird. And so I'm wondering like this kind of like say exponential density ratio, how can we construct something like that so that we still have an analytical solution for your game? Yeah. Yeah. Oh, yeah. We could have like very weird distributions, right? Yeah.
So basically, but far away. Um, so in two cases, things like it's like 0, and then the data is just like not useful at all. And which is reasonable in some cases. For example, if our if the target made by really, really far, and then so data is not that meaningful, it's really really small, then the target the training data in this case this will be weighted very low, and then in the regression problem you basically need to depend on your base distribution. That's why we have something here. So that means the data is this part is not that meaningful, it's too far, and then you may need some prior knowledge to guide you through this thing. So I think currently learning theory even in this case is try to figure out what the conditions that we can really extrapolate, really generalize to the different distributions. I think we still have a lot of open questions here. And in this case, we're still the target need to be like relatively close, and they still play extrapolate. Otherwise, we depend on the prior knowledge, and this part can be just uniform distribution, for example, this also random distribution, like distribution is 0. I think. So yeah, I think we're still working on it, but it's very good.
Okay, sounds good. Yeah, one more question. So in your experiments, I'm not quite sure why the GP is not performing really well, because it's like this is kind of a low dimensional problem and it shouldn't affect the kernel, right?
Then I think also a lot of other literature with like if it's a wide reading, then people try to only look at the average dimension independently
Yeah.
and try to just single out
Different kernels, yeah.
but and then you have the parameterization and you do not need to like single out that each part. So yeah, we see certain
Okay, sounds good. Thanks.
So I was curious about the density estimation part. So that seems like a hard problem when you have like high dimensions. So what kinds of techniques do you use, and what kind of dimension do you expect this to be able to handle?
So yeah, this density for finding all the dimensions, and I think our case is looking for this. Well, I have another paper in condition case where this X are like pixels, which is like 100 by 100 kind of like matrix. And in that case, we try to in your network try to do the density ratio alongside with the latest problem, and then make the exact framework. And we can talk about that like later. But there is other ways we try to overcome this dimensionality, and it's true it can be a bottleneck sometimes. And then with tools of deep learning, hopefully we can resolve that problem. So there's some progress there I can share. But yeah, currently, if you want to do this two-step thing, you first estimate this and plug in, then usually it works on the dimension.
Okay, so we have 2 questions in the chat that because they cannot ask offline. Ming Song is asking that how does the training learning algorithm work? Like if you want to train, I think the adversarial algorithm, how does it work?
I see. So yeah, I didn't really include a lot of details, right? When I say like derived learning algorithm, and then in this case, after you have this time parametric form, basically the only parametric change is data. And data you can learn using a gradient descent or a gradient descent. So after after this, so this is a really convenient form. So after you have this kind of exchange and develop this form, now you do the data by.
But so basically you have some data from, like during train time, you have data from your source and your target distribution. So you know where you want to extrapolate into.
You only have labeled data from source.
Okay.
From target, that the target data is only used for estimating risk.
This-
Otherwise, train data is not used.
Okay, okay. And then there is another question by Haruki. Does the proposed framework induce active exploration? For instance, does the learner have a sense of which region in the state space is more informative to collect data from?
Yeah, that's a very good question. Here is basically the active learning kind of framework. And we'll assume that you can choose the next kind of domain you want to tap into.